Okay, so in section 5.1, we talked about the basics of this DC motor and how it worked. And really what we're looking at two voltages that are in play. We have the source voltage that is supplied to the armature of the DC motor. And then what happens is that armature starts to turn. Now, the whole of chapter 4 was all about this voltage that's generated because an armature is turning. So what we found out is it doesn't matter what causes the armature to turn, but when it does turn, there is a voltage that is developed, okay? So what we're looking at now in section 5.2, which is called acceleration of the motor, is a way to quantify these actions that are occurring with this DC motor. So let's look at that in some detail and come up with some equations and start thinking about particulars of what's going on here. So what we're told on page 97 is that the net voltage acting in the armature circuit as given to us in this figure 5.2 is this. It's the source voltage minus the voltage that is developed on the armature, okay? So what we're going to be able to do is we're going to work with this, okay? And so here's source voltage and here's armature voltage, and we're going to work with this portion of what's going on. And notice again that the source voltage is opposing the armature voltage, or you could say that, you know, the armature voltage is opposing the source voltage, whichever way you want to term that. But you see that they are opposing because the polarities are the same. So what we can do is we can determine this current in this circuit by saying that the current is equal to E sub S minus E sub O, source voltage divided by armature voltage, divided by the resistance in the circuit. And the resistance in the circuit consists of the copper losses that occur in the actual armature conductors, okay? So anytime we have, you know, conductors, they're going to have some small resistance, and that's what we have here. So what we're going to do, and this is really our first equation here in chapter 5 that's new. We also had equation 4.1 earlier that told us about the armature voltage, you know, but we actually borrowed that from chapter 4. So here's our first new equation, 5.1. And so it says the current is equal to the difference in the source and armature voltage divided by the resistance of the circuit. So he says, let's walk through this through different conditions and see what we can come up with. All right, so the first thing we're going to get is the starting current. Okay, so the starting current for this DC motor, and this is a particularly good thing to know because we're going to look at later why these electric vehicles are able to accelerate so fast. And what we're going to find out why is this exact thing right here, because the current at startup is simply going to be the source voltage that's applied, and since the armature isn't turning yet, there is no armature voltage, so the starting current is simply E sub S divided by R. Now he goes on to tell us that the starting current can be 20 to 30 times greater than the nominal full load current of the motor. So, you know, in practice, you know, you couldn't have this for very long because breakers would trip and fuses would blow and all this sort of thing would be going on. But what happens is you get this very rapid acceleration with this incredible torque, but it doesn't last for long. It's just this immediate thing, because as soon as all this starts to occur, this armature starts to turn, and when the armature starts to turn, then the E sub O is going to develop, and it's going to cause this current to go down very fast. Okay, so again, we're calling E sub O this counter electromotive force, and it will start to develop as soon as the armature starts to turn. And the faster that it turns, the greater this armature voltage is, and the less the current is. All right, so very typical explanation, or just a characteristic of the DC motor that we want to be able to follow. Now, although he tells us that this armature current's decreasing, the motor is going to continue to accelerate until it reaches this definite maximum speed. At no load, this speed produces a counter electromotive force that's only slightly less than the source. And if these two things, source and armature voltage, were to be equal, then at that point, the net voltage would be 0, and so would the current. And then when that happens, this thing isn't going to happen. So what happens when this thing reaches what we'll call equilibrium? The E sub S will always be slightly larger than E sub O. At full speed, it may be not more than a few volts, but it's still enough for the motor to be able to draw current, and so this motor action continues to happen. Okay, so that's the basics of that. And then sort of to finish up with this, why is E sub O always a little bit less? Well, there's certain things that cause the voltage to drop. There's the drag caused by the fan and the bearings, there's also that slight resistance, and all of that factors into that. And so the armature voltage is always a little bit less than the source voltage. He says as the speed decreases, the net voltage increases, and so does the current. The speed will cease to fall as soon as the torque developed by the armature current is equal to the load torque. So what you have this feedback going on, this back and forth, right? So if I increase the load, the motor's going to slow down. If the motor slows down, the current increases. If the current increases, the motor speed is going to increase. And so it's back and forth, and so this is at play constantly. And he finishes this section up, this 5.2. He says, when a motor runs at no load, the counter EMF must be slightly less than E sub S, so to enable a small amount of current to flow sufficient to produce the required torque to make the motor turn. Okay, now let's do a little pause here, and then we're going to work a problem that's going to take all of this into consideration. All right, so quick pause here. And maybe I should have made 2 videos out of this, but we'll just plow on through and make it one. But this is example 5.1. And this in the text that I have still on page 97. And he says in example 5.1 that the armature of a permanent magnet DC generator has a resistance of 1 ohm. Okay, and we can find that right here in these drawings of this DC motor that we're working at. Okay, so that represents the resistance, the armature resistance, the resistance that resides in those conductors. Okay, so it has a resistance of 1 ohm, and it generates a voltage of 50 volts, when it's rotating at 500 RPMs. Now, Mr. Wilde in this textbook is going to make great use of something that I call just a proportion, right? So, and what we're going to assume, we're going to assume linearity. And what do I mean by that? I mean this old thing from math class. We're going to say directly proportional, right? Straight line kind of stuff. And, you know, for a lot of the stuff that we work with, that's going to be very accurate. A little bit later, not so accurate. But, you know, for this, we're going to assume at 50 volts, it's 500 RPMs. Now, what does that mean? Well, what that would mean is at 100 volts, and that doesn't look like a zero, at 100 volts, I would be turning at 1,000 RPMs, okay? So, you know, it's directly proportional. So that's all I'm saying. And so we're going to work off of that and be able to do some calculations based on this idea of proportion, you know, putting some of this basic math that we learned to work. He says if the armature is connected to a source of 150 volts, calculate the following. Okay, so here's our source of 150 volts. And now he wants to know, A, the starting current. All right, what is the starting current? Well, let's take these and bite them off one at a time. So the starting current, our equation for current says I is equal to E sub S minus E sub O divided by resistance. Now we're going to put some real values in here. I've got 150 volts, he says, as my source. Since this is at startup, there is no armature voltage yet, so I'm at 0 volts. So I'll put that like that. I've got a resistance of 1 ohm. So at startup, our current is 150 divided by 1, or 150 amps. And he's trying to show us that with that right there. Okay? Good enough. And that's part A of this thing. All right? The next thing. All right, we gotta use this relationship that we have where we're told that 50 volts is equivalent to 50 RPMs. And he says in part B, what is the counter EMF? Okay, to work that problem, we got to know that counter EMF is equal to the armature voltage. And I want to know what that is when the motor runs at 1,000 RPMs and what it is when it runs at 1,460 RPMs. Okay, well, I can do that because, you know, to begin this thing again, he told us that it generates a voltage of 50 when it's at 500. So look, I'm just going to set this up like this, 50 volts, 500 RPMs. And I'm going to make an equivalence of this because he says, what is the voltage at 1,000 RPMs? We kind of already did this, didn't we? But anyway, and so we'll set that equal to X. And so 1,000 times 50, right? And solving this for X, so 1,000 times 50 divided by 500. Let's get rid of some zeros, right? There's one I'll take away from here, and here's one I'll take away from here. And so I end up with 5 into 100. And so that's, you know, what I'm trying to get for X. And that will give me the voltage there that I need. Okay, so let's see, what have I got? 5 times 100 is 500 divided by 5, which would give me, oh, drawing a blank, help me, where am I? 5 times 100, 500 divided by, that should be 50 amps, right? Excuse me, 50 volts. Okay, so the net voltage there is going to come out to be 50 volts at 500 RPMs. At 100 volts, it would be 100 volts at 1,000 RPMs. Okay, so excuse me for stumbling through that, but gosh, that's a lot easier than I made it, right? Simple relationship. And then the other one, can't quite do that in our head, But let's say if we know 50 volts, 500 RPMs, what would it be at, lost my train of thought, 1460 RPMs, what would the voltage output be? So 1460 divided by, multiplied by 1460 multiplied by 50 divided by 500. And what would come out with there is that we would find a voltage of 146 volts would be equal to X. Okay, so that simple proportion there to give us these numbers. So here's our 100 volts at 1,000 RPMs and 146 volts at 1,460 RPMs. And again, we could do that for any value we wanted to put in this, and it would work out because we're basing this on a absolute proportion. Okay, so that would be part B of this problem. And then part C says, what is the armature current at 1,000 RPMs and what is it at 1,460 RPMs? Okay, so 1,000 RPMs equated to 100 volts, E sub O, and let's go ahead and put this one down, and 1,460 RPMs equated to 146 volts, E sub O. Now, I can do these remaining problems because, he's asking, what is the armature current at these different voltages? So I've got I is equal to E sub S minus E sub O divided by R. E sub S stays at 150. For the first one, it's 100. And of course, this stays at 1. So for the first armature current at 1,000 RPMs, this is going to come out to be 50 amps. Okay. Then for the second one at 1,460 RPMs, the E sub S still at 150. E sub O is 146 divided by 1. 150 minus 146 is 4 amps. So what we're seeing is, as this speed increased, the current went down until we reach a certain condition. And we'll talk about what that is a little bit later. And he says, under these conditions, the armature current is only 4 amps, and the corresponding motor torque is much smaller than before. So remember, more current, more torque. Less current, less torque. Very important concept as we talk about motors. All right, this one drug out a little longer than I wanted to, but that is section 5.2.